Welcome to the second video in Unit 3. We're still working with conic sections. The previous video talked about a circle, and today we're going to talk about the parabola. You'll notice on this graphic, a parabola is the intersection of a plane with a double-napped cone, and you can see its value here. We've also done the circle. Notice that it's a horizontal intersection with the cone to make a circle. You can see the ellipse, and then later on we'll be doing the hyperbola. We're going to do all four conic sections. I know, I'm out of control, but here are a few parabolas. Parabolas are everywhere in nature. We see them everywhere. They're in man-made things mostly, but they're also in just regular nature. For instance, if you're looking at this flashlight, the inside of the flashlight is in the form of a paraboloid, which is a three-dimensional parabola. And so that's how you have the directed line segment, radar dishes, the arch, in St. Louis, and then, of course, the golden arches. But here's some other interesting parabolas. Although this arch right here could be argued to be half of an ellipse, but for the sake of what we can see something that's also a parabolic shape, this roller coaster, the waveforms. And then this is the Library of Congress, and it's a dome, but this area right here looked a little bit parabolic. It might be ellipsoid too as well. And these, of course, are my favorite parabolas. You've got a suspension bridge with tension and compression. And of course, in Horton, here's a who. Okay, here we go. We're getting down to the nitty-gritty of a parabola. And we're going to add parts to it. We've seen parabolas before. Parabolas are the result of a quadratic equation. We've worked with quadratic equations now for a bit. Now we're going to look at parabolas that are not only functions, but parabolas that are not functions. You can see here that this parabola actually passes the vertical line test and therefore is a function. However, this one that's drawn here does not pass the vertical line test and is therefore not a function. It is, however, a parabola. So we have parabolas that are that are up, right? Functions that are up are even functions. We can also have parabolas that are upside down, reflections over the x-axis. We also know that parabolas are symmetrical about an axis. Here's the axis of symmetry. This one also has an axis of symmetry, right straight through the vertex. The vertex of a parabola is HK. We saw that with the center of a circle. They're going to use H and K to denote the center, and also the vertex of a parabola. A parabola is formed, and you'll see it on the next slide. The distance from the focus to a point on the parabola is the same distance from the point on the parabola to this line down here called the directrix. So if I picked any point on the parabola and I measured it to the focus and measured that to the directrix, it would be the same distance. And so the infinite number of points along the parabola have that same property. The other thing that's probably most important and that we're going to be using exclusively and often is this property of a parabola in which the distance from the focus to the vertex is the exact same distance from the vertex to the directrix. These are the same length every time, always. Okay? And so we denote that distance with the letter P. So the focus to the vertex are exactly P distance from each other, and the vertex to the directrix is the same. And so on this other one here, this is the focus right here. This is the vertex, right? This one, which is not a function, this parabola, which is not a function, is also does not have a max or a min. Do you see that? Because it's not a function. But the distance from the focus to the vertex and the vertex to the directrix are the same distance, and that is p. Now, you'll notice that the directrix is a line. The focus is a point. The vertex is also a point. So in other words, if I were going to write the equation for the directrix, because it goes through the y-axis, it will be y equals, if it's a horizontal line. If it's a vertical line, it's going to be x equals. Remember that it goes through the x-axis, therefore it actually has an equation. Those are some important things to remember, and I hope you've taken the time to write them down. So here's a graphic that shows the two things I was talking about previously. For instance, here they show the distance from the focus to the vertex, vertex to directrix, and they don't call it P in this particular thing, they call it A. It doesn't matter what you call it, it's the same distance both places. So for instance, like a puzzle, if I know where the focus is, I know exactly where the directrix is because they're the same distance away. The second graphic shows the other thing I told you about. To form a parabola, you measure the distance from a focus to the point, and the directrix to that point will be the same distance. And you can see how it does that as well. So these are neither one functions, but this gives you a good idea of the two things that I was talking about before. Please make note of these characteristics. They will help you so much when you're getting ready to graph these. Okay, so here's our most important slide here. We have the equations of parabolas in standard form. These, of course, are in standard form. So we have a parabola that is either an up parabola or down, right? This is the one that we've been graphing. We've graphed a whole bunch of these. That will mean that when you have an equation of a parabola, remember that parabola, only one of the variables is squared, the other is not. So that's how we told the difference when we did the very beginning part. Notice we have an h and a k. H always goes with x, k always goes with y, and p. Do you remember p? 4p is part of this. This is 4p, but p is the distance from the focus to the directrix. It's also the same distance from the directrix to the vertex. The vertex is at hk. If you'll note here, the vertex form of a parabola looks like this: y equals a, x minus h squared plus k. It looks very similar to what we have here. So if you were to solve this particular equation to make it look like this one, in other words, I would subtract the k to this side, right? We're getting close. But the 4p is with the y, so you would divide. So a is going to be equal to 1 over 4p. Conversely, you could also say that 4p is equal to 1 over a. So be sure and write these down. All right, the only difference between an up or down parabola and a side-to-side parabola is that y is squared instead of x. So it still has this. Notice that the h still goes with x, the k still goes with y, and then we have 4p is here, and 4p is still going to be 1 over a. The vertex is at hk. Remember, it's kind of backwards when you have the y squared. So be sure and write this down. This is really important. So here's an example of how we might use the equations on the previous screen. If we're told that we have a parabola that opens upward and it has a vertex at 0, 0 and a point at 2, 9, we can find the equation of a parabola using the equation that we were given. So since it opens up, I have x minus h squared equals 4p y minus k. Well, h and k are 0 and 0. So instead, I'm going to have x squared equals 4p y. The other equation, the other point that they give us is the x and the y. I need to solve for p, or at least 4p. So I'm going to put in 2 for x. I'm going to put that together. and y is 9. So I have 4 equals 4p, and I'm going to keep that together, equals 9, divide by 9, and 4p is going to be equal, that's 1, to 4/9. So if I rewrite this, I have x squared is equal to 4/9 y. Now, I didn't divide by 4 and solve for p yet because I don't really need to do that yet unless I'm going to graph it. Okay, so I am going to graph it. So if 4p is equal to 4/9 and I divide by 4, that's going to be 1/9. Now, wouldn't it be lovely if they were these beautiful little numbers? But they're not. So I'm going to put in the vertex at 0, 0. And then I'm going to make 1 really high up here because p is 1/9. I'm assuming that's about here. That's the focus. This is the vertex. And guess where the directrix is? It's about 1/9 this way. So this is at y equals negative 1/9. The focus is at 0, 1/9. And the vertex is at 0, 0. Draw it in, and you're good. This would be a different problem if I told you it opened to the right. The only thing that would change really is that I would have y squared instead of x squared. Okay, here's another example. It says to find the equation and graph. So what I find it easier to do is to go ahead and graph it, and then from the graph figure out what my equation needs to be. So I'm going to put the vertex here. It says that the directrix is at y equals negative 2. So this is negative 2. We remember that the parabola never crosses the directrix. It opens in the opposite way from the directrix. So it's going to open this way. I know that the distance from the vertex to the directrix is p. P is 2. The vertex is at 0, 0. So I know that the focus is going to have to be right here, right? Because it's 2 away in the opposite direction. So 0, 2, this was y equals negative 2. All right, so I do know that opens up. So this is x squared equals 4py because the vertex was 0, 0. And I know p is 2. So x squared is 4 times 2y. And I know it's 2 because that's the distance. So x squared equals 8y. And that's my equation. So I did it a little backwards. I graph first, and then write the equation. And I often do that because just looking at it, it's the easiest way I know without having to memorize a whole bunch of formulas. Okay, here's our final example. We're going to put this equation that's in general form into standard form and then graph it. All right, so the first thing we want to do is we want to rewrite this. I'm going to leave the part that I'm going to complete the square on the left side, leave a space, and then I'm going to subtract the 8y and the 9 to the right side. From there I'm going to complete the square. So I have x minus, take half of 2 and get 1. 1 squared is 1. So I'm going to add that 1 to both sides. And then combine like terms. So I have negative 8y minus 8. Almost there. I need to do a little bit of factoring out. So factor out a negative 8. Double check, negative 8y minus 8. And now I have this in standard form. The x is squared. The x is squared. So this is going to be a parabola that goes either up or down, right, because of the x. And then I look here at this number. This number is negative, so I know that my parabola is going to go down. So the two things we need to graph, we need to know where the vertex is, and then we need to know P. Now that we know the direction of the parabola, I find the vertex. The vertex is at 1, -1. And then 4P is equal to -8, so P is equal to -2. The negative is telling me that it goes down. So that's just another confirmation about what I need to do to graph it. So I'm going to draw this graph, and let's put in a few. Okay, the vertex is at 1, -1. So I go over 1, down 1. That's the vertex. I know that it's upside down, so the directrix is going to be on the top. So I'm going to go up 2, 1, 2, and draw in the directrix. So my directrix is going to be at y equals 1. The vertex is at 1, -1. The focus is going to be 2 down from here. So my parabola is going to go down, and then I just need to write the point for the focus. And the focus is going to be at 1, -3. And that's how we do that. So in class, we're going to be working with parabolas, and so be sure to refer back to these examples. See you in class.